Okay. So we are starting on the next topic, which is actually electromechanical energy conversion. Okay. So far what we had seen in terms of electrical machines is transformer, which is basically a static machine. There is no rotation, there is no movement involved, and that's the reason why the air gap was very, very less, and if the air gap is less, the magnetizing current is also normally less. That's what we talked about earlier. So compared to a transformer, if we look at any other moving mechanism, which is a rotating machine or translational machine, all those things are going to definitely have some amount of air gap between the stationary part and the rotating part. So that is going to definitely ask for more amount of current. If flux has to flow through the air gap also, it will require more current. So as a rule, any moving mechanism is going to demand more amount of magnetizing current as a rule, right? So we are going to look at, actually if you look at electrical to mechanical energy conversion, one of the examples is an actuator or a relay. What do we mean by an actuator? If let us say I have some structure like this, I'm just going to arbitrarily take a structure which is somewhat like this, and I want some other piece to come and close this gap. And this gap is normally a lot. It is not going to be closed at all. But if I want this to be closed only on some instigation, some stimulation, I don't want it to close otherwise. So I'm going to have a moving part which is also probably made up of iron, and it is probably going to be connected to a fixed frame somewhere through a spring. This is not an inductance, because as an electrical engineer we always think it is an inductance. Let's say it is not an inductance, it is a spring. The spring is holding probably this piece of iron at some point which is away from this particular C-shaped magnet. So if I actually have a coil around this C-shaped magnet, and if I pass probably a current I through this, only when I pass a current, this C-shaped iron piece is going to get magnetized and it will attract this piece of iron. If I may say, this is also made up of iron, that is going to be attracted. So if it has to be attracted, the current should be strong enough to nullify the action of a spring, and it has to dominate over the spring's mechanism. Only then it will be able to pull it. So this is generally known as an actuator. The actuator is a mechanism which may have a translational movement depending upon how much current you are passing through another mechanism which is creating a magnetic field. So this is essentially an electromagnetic actuation mechanism. This is also sometimes called as a relay. A relay typically is used for some protective features in a power system. For example, if I have a power system which is supposed to be carrying 1000 amperes of current. If the current goes more than 1000 amperes, say it goes to 1200 amperes, then immediately a protection system should act, because it should sense that there is some overload somewhere. Something has been short circuited probably. So the current drawn is heavy. If the current drawn is heavy, I have to make sure that somehow that circuit is cleared. So unless the fault is cleared, I can't activate again that particular load. So the moment it senses a overcurrent, it should immediately open up some switch. So that is what happens in our home also in terms of many circuit breakers. You might have seen in the mains box, The circuit breakers generally act as soon as maybe there is an overcurrent. So if there is a short circuit sensed in any of the rooms or any of the loads, immediately it will open out. So what happens there is also generally a relay or actuator mechanism. The moment the current goes beyond a particular value, immediately the magnetic pull becomes quite a lot, because of which some switch is opened or some switch is closed. That is what happens. So these are typical examples of translational motion or linear motion using electromagnet. But what we are going to concentrate mainly is on rotational mechanism. And you should also realize that this kind of actuator or relay is a one-time process. Maybe if I need protective feature, once it will act, again it has to be reset. Maybe another time when the fault happens, it will again act. It is not a continuous energy conversion. Whereas generator or motor is a continuous energy conversion mechanism from electrical to mechanical or mechanical to electrical. We are going to have continuous energy conversion mechanism taking place in rotational machines. So what we are going to concentrate specifically is electrical rotating machines which will actually have continuous energy conversion mechanism. Right? That is what we are going to look at in this particular course on the whole. Until now what we talked about was only a static machine. Transformer is also very much a machine, but it is a static machine. So what we are going to look at now, from now on, is rotational machines. Right? So I can have actually on one side, I can have electrical energy input. And it is going to go through a magnetic via media, because actually the magnetic medium is not going to contribute towards any energy directly. It is only serving as a conduit between the electrical energy and mechanical energy. So if I am having electrical to mechanical energy conversion, I am going to have the mechanical output ultimately. Now this is going through magnetic via media, so we will call this as actually the motoring operation. When electrical energy is converted into mechanical energy, we call that as motoring operation. On the other hand, if I am actually giving mechanical energy as the input, and we are going to have ultimately electrical energy as the output through the magnetic via media, again we call this as the generator operation. So we will be looking at both of them. Please understand that the same machine can work either as a motor or as a generator. Only thing it requires is either electrical energy input or mechanical energy input, but there should be a magnetic via media which will also be present for sure. So the magnetic via media, what we are actually looking for should be in the form of an electromagnet, and we call that system as field system. And where the electrical energy is given as input if it is a motor, or from where it is taken out as the output if it is a generator, we call that portion as armature. So specifically we are going to have two portions in the electrical machine. We are going to have one of them as field system. The other one we call that as armature system. And when we are looking at field system, it can be actually the stationary portion or it can be the rotational portion. No problem. The same way armature could be stationary, armature could be rotating. It depends upon what kind of mechanism I have designed. For example, if I am going to talk about DC machine, normally we would see the field system to be the stator armature system to be the rotor. Whereas if I am looking at basically synchronous machine, for example, which we will be talking about towards the end of the course, the field will be housed in the rotor and armature will be housed in the stator. It doesn't matter, even if it is the other way around, it would work. But for convenience, for logistics purpose, generally we tend to arrange the two different systems in two different portions like this, right? So it need not be the case that I have to have field in the stator or I have to have field in the rotor. In fact, in some of the electrical machines that are there in our machines laboratory, which is there in second block, we have synchronous machines having the field system actually in the stator and the armature in the rotor, and it still works. It's a laboratory, so anything goes. It doesn't matter. We are not going to look at optimization of design and things like that. It is essentially to demonstrate that either way it will work. That's the reason it is like that as far as our electrical machines is concerned. So let us say I have, first of all, in electromechanical energy conversion systems, right, I am going to have mainly three portions being looked into. One is the electrical input. Whenever I am talking about an electrical input, that means I have certain voltage applied, there should be some current flowing, because of which there will be definitely some I square R losses as well. So correspondingly, the losses in electrical input system will be I square R losses. Similarly, if I look at the magnetic wire media, normally I may see that there is some increase in the field energy also. Electrical energy we know is VI dt or EI dt, right? Whereas if I am talking about field energy, obviously it should be associated with inductance. So half Li square typically. That is what we are talking about as the energy that is associated with the field or magnetic field. But along with that, I may have core losses, what we talked about already in transformer, that is due to the magnetic field. And core losses generally will be associated with the machine only if I am talking about alternating currents. Right? We already talked about this, hysteresis loss and eddy current loss we will have only if there is alternating current. Otherwise we are not going to have those losses. And the third type of subsystem which is a part of electromechanical energy conversion system is the mechanical system. So the mechanical system again will have the losses as actually friction and windage losses. These are the two losses that are going to be there normally with any mechanical system. Friction, I am sure all of you know. What is windage? Any idea? What is windage? Friction, all of you know. What is windage? Windage is associated with wind. Wind. So, if I am running the machine in vacuum, I will not face this problem. But unfortunately, we don't run the machine in vacuum. We always run it in an environment which is probably filled with air. Right? So, when the machine is rotating, right, it has to definitely displace the air, surrounding air. So, that air is going to offer some resistance to the movement of the machine. That particular loss encountered because of the presence of air or wind, surrounding wind, that is known as windage. And this will be more if the machine is trying to rotate faster, because it has to displace the wind more. So it is like fan. When you have the fan rotating much faster, you see that more and more wind you get. Right? So generally you are going to see that this particular windage is always dependent upon the speed at which the machine is rotating. If it is rotating at lower speed, the windage losses faced by the machine will be smaller. If it is rotating at a higher speed, you will see that the windage losses are more. And in general, empirically the expression we can say the windage loss is actually proportional to, if I write it in the form of torque, so T windage I am saying, the loss torque associated with windage. Normally we talk about the losses in the form of watts, right? But here I am talking about it in the form of torque. So the windage loss is proportional to omega square or speed square. So I should say power associated with windage or the power loss associated with windage will be proportional to omega cube, because T multiplied by omega is what is the power, right? So I can say that T corresponding to windage will be proportional to omega square, or the power corresponding to windage will be proportional to omega cube. Where is the velocity of the wind? It is, let us say I am just having, in a room, I am rotating the machine, right? The wind is really not, we are not expecting it to move just like that. It is almost still, because of which you will get omega. Directly, whatever is the rotating speed, that will become omega as to calculate whatever is your loss torque or the power. If you are, for example, looking at an elevator which is probably going in Sears Tower, right, which is having a huge height, like 112 floors. So it is going to go through the entire height in a fraction of maybe a minute. So which means it has to tear through the wind column and then go. So very, it will be very realistic to model that as, a windage kind of torque, because it will be proportional to the velocity square, at what velocity it is going. Because frictional losses will not be directly proportional to whatever is the velocity square. So we are essentially looking at two components. One is like a static friction. In fact, friction itself we will be looking at different things. Viscous friction will be proportional to omega. Static friction will not be dependent upon omega at all. The third static friction is the initial frictional component which will be required to move, give the initial momentum. And the third component is windage. So you will have essentially, there are three components if you want to really do the hair splitting completely for all the frictional quantities. Right? Okay. Leakage flux. In the case of the magnetic field. See, in the magnetic field, if you are talking about leakage flux, that will be actually counted as the voltage drop more than any power loss. Am I right? It will not be counted into the power loss. We are talking mainly about the real power losses. Whereas if you are talking about iron loss, that is clearly real power loss because it will contribute to heating. Whereas leakage flux is not going to contribute towards heating, it will only go into voltage drop. Am I right? Okay. So normally we should write, if it is a motoring mechanism, dWe, which is the electrical power input for a short duration, that should be equal to whatever is the increase in the field energy plus whatever is going to be increase in the mechanical energy. Plus, of course, losses. I have to include all the losses. And this is true for a motor because we are giving electrical energy as the input. If I am writing this for the generator, I have to write dWm is equal to dWf plus dWe plus losses. Because in the case of generator, what I am giving as the input is mechanical energy and what I am getting as the output is electrical energy. And whatever is the increase in the field energy, that is just incidental. I'm not intending to really do it, but it is just incidental. I'm not going to really strive hard to increase the field energy. What I want is actually conversion from mechanical energy to electrical energy or electrical energy to mechanical energy. I'm not interested in increasing the field energy, but if the air gap is decreasing, maybe the flux will increase, due to which maybe my field energy will increase or decrease. That is just incidental. It is not really going to cause specifically, intentionally any increase in field energy at all. What I am worried specifically about are these two. And I would like to minimize the losses as much as possible. Right? So let us try to first of all see, with this background in mind, whether we would be able to get an expression for electrical to mechanical energy conversion process, whether we would be able to get an expression for force or torque. How do we really go about doing it? That's what we are going to do in this particular chapter. We are essentially trying to look at how electrical to mechanical or mechanical to electrical energy conversion takes place and whether we can get an expression for the torque or force, so that we would be able to utilize it later. So let me first of all take the same mechanism. So we are first of all going to understand very clearly what is field energy. We have still not gotten clearly what is the field energy. We know half Li square, that's all. But how are we really going to quantify it? That's what we want to check it out. Okay? So for this, let me again take the same mechanism as what probably I drew earlier. I am drawing more like a C here, right? And then maybe I have one more piece here. There are two pieces. Both of them are made up of, say, magnetic or ferromagnetic material, right? And let's say this is connected to a frame which is a fixed frame through a spring. Fine? Now I am going to have a coil wound around here, which is going to be passed with the current I. Fine? And when actually I am applying a voltage V, probably I will have a current I depending upon what is the resistance, right? And what is the inductance. If it is DC, for example, I can say V by R is I directly. If it is AC, I am going to have definitely an inductance drop also, and there will be an induced EMF E on the other side. Right? That is the induced EMF. Now, let us say the distance is something like X. This is the distance X that I am having as the air gap. Okay? Now, when actually the current was not flowing, still maybe I was having the distance of X. And when the current is flowing, if the current is not strong enough, I am definitely going to have still that distance maintained as X, because the spring is going to hold it at that particular place, whether we like it or not. So, if I try to actually plot as I increase the current, right, how my flux is increasing, or I may write N times phi, how that is increasing. Either way is fine. N is number of turns. So I am just multiplying the flux by the number of turns, and I am calling that quantity as lambda, because we normally write N d phi by dt is equal to E. So I am going to write N phi as lambda, and I call this as flux linkage. How many times this flux is linking with, the total magnetic path. So this I am calling as N phi. Right? So if I plot this, we know basically that I am going to have, as I increase the current, it will increase and it will reach some saturation. This is what is our magnetization characteristics normally. If I am talking about x being larger and larger, if the distance is larger and larger, very clearly it is approximating itself to larger and larger air gap, and the air gap reluctance will dominate over whatever is the reluctance of the ion path. So it will become more and more linear. If I have larger air gap, I'm going to have more and more linear characteristics. If I have smaller air gap, I'm going to have more and more non-linear characteristics because of the ion coming into picture, and whose reluctance is dominating, I have to look at it. Right? So if the air gap is smaller, I'm going to have highly non-linear magnetization characteristics like what we saw in the case of transformer. This is how it is going to be. What I am giving as the electrical energy input, let me try to see. That will be E times I times dt, because I am minusing the I square R losses. I don't want to take that into account at all. Right? I square R losses are not going towards any energy conversion. It is just dissipated in the form of heat. So what comes out as the induced EMF E essentially is towards the inductance. It is going towards the inductance of the coil. So I am writing EI dt as the electrical energy input. If I just neglect all the other losses in mechanical form or core losses and so on, I should have dWe equal to dWf, we wrote this earlier, plus dWm. I am neglecting the losses, so I am not writing the losses at all. So this is actually the mechanical output, and this is the field energy, or increase in the field energy. I have not really mentioned about any movement so far, because I have not really sufficiently pumped in, enough amount of current. So it was not able to attract the other piece of iron. So there was no movement at all. So if I look at how much is the mechanical energy output when there is no movement, this will be 0 in the absence of movement. So whatever I supplied, the entire thing went towards increasing the field energy. That's what it is indicating. Right? If I don't see any mechanical output, whatever I have given as the input of electrical energy, which was EI dt, that entire thing has gone towards actually creating, only the field energy. So if I am saying that, I should say EI dt incidentally becomes my dWf. Right? And E is after all d lambda by dt. So I should be able to write this will be d lambda by dt multiplied by I dt. So this will give me essentially I d lambda. So I d lambda in the absence of any movement gives me directly whatever is the field energy that has been accumulated for a small duration dt. So just to tell that graphically, if I am looking at a particular value of I, and if I am looking at a small variation in lambda, this strip actually gives me the area under that strip, in the left side of the curve, which is the magnetization characteristics. This is going to give me what is dWf. So the field energy is given by the expression I d lambda integral, provided I don't see any movement at a particular position of maybe the entire magnetic circuit. I should be able to say, if I get integral of I d lambda, I would be able to get the field energy. So for example, if I am looking at a particular lambda value here, maybe this lambda is, let us say, lambda 1. I should be able to get WF at lambda 1 flux linkage for this magnetization characteristic will be from 0 to lambda 1 I d lambda. That is what will give me what is the field energy associated with that particular magnetic circuit when it reaches a flux linkage of lambda 1. Right? So this I can again express it in terms of magnetic circuit quantity. I have two specific magnetic field intensities, let us say associated with the core and associated with the air gap. Let's try to look at the magnetic circuit again. This magnetic field lines are going to flow like this, and then flow like this and come back. If I take the average length, I should say LC is much higher because LC consists of all this length, and all this length and this length as well. All that correspond to ferromagnetic core. The gap lengths are only this much. This is Lg, this is also another Lg. That's it. Right? So I'm going to have the gap length to be really, really small, whereas the actual core length is going to be much larger. So the magnetic circuit length on the whole is Lc plus Lg. Maybe I can call this as Lg by 2 and this is also Lg by 2. Together it becomes Lg. Right? So I should be able to write that if I try to look at the MMF in this case, this MMF will be N times I, which will be Hg Lg plus Hc Lc. This is what is the total MMF that is going to be associated with this magnetic circuit at this point in time. Right? So I should be able to write, now I want to express ID lambda in terms of magnetic circuit parameters. That's why I am going through this. Okay? So I can write basically I is equal to, because I wrote already Ni equal to HClc plus HgLg. So I can write I equal to HClc divided by N plus HgLg divided by N. Right? So I should be able to substitute that I here. So I don't have to write I again. But let me write for d lambda. First of all, we wrote lambda as N times phi. Let me write this as NBA, where area is A is the area of cross section of the core. I am neglecting fringing. So I am assuming that the area of cross section is everywhere the same. Okay? So this is A. So NBA. So if I write d lambda, if I assume that the area is a constant, it is not having any deformation, NAdB. Right? I should be able to write this. So let me write this ID lambda as, first of all, I is substituted with HClc divided by N multiplied by d lambda, maybe this is NAdB. Right? That is the first portion. And another portion is going to be HgLg divided by N multiplied by NAdB. Right? So I should be able to write it like this. Let me assume maybe the flux density, whatever I am looking at for the core, I should be able to write, first of all, let me cancel these, and A into Lc I can write as the volume of the core. right? And I should be able to write similarly, this N and this N are cancelled. A multiplied by Ng, I should be able to write volume of the air gap. Right? So I can say Wf, which is equal to integral I d lambda, will be, in this case, Hc will be whatever is the flux density divided by, I can say probably mu of the core. Mu of the core. Right? And I should be able to write multiplied by dB probably, and or I can retain it as it is Hc, but I have just replaced it by B by mu c. That's all. And the next one I can write this as B divided by mu naught multiplied by dB. The whole thing multiplied by, of course, here I have to multiply this by volume of the core, and I have to multiply this by the volume of the air gap. Now, I can definitely write this is B square by 2 mu naught when I am actually integrating it over, the entire region of the flux density. I should be able to write this as B square by 2 mu naught multiplied by the volume of the air gap. Here I will get maybe B square by 2 mu c, but please note, mu c is going to be much higher as compared to mu naught. So, the field energy associated with the air gap will be much higher as compared to the field energy associated with the iron core. Because to magnetize the air gap, I will require much more amount of, current and power to be pumped in as compared to what would have happened for the iron core. Yes, you have to multiply by the volume also, but if I look at the overall energy that is associated with the air gap, although the volume is really small, generally the energy associated with the air gap is going to be outweighing whatever is the energy associated with the iron core. I agree that iron core volume is higher, no doubt. But because of the fact that the permeability is really small for the air gap as compared to a normal ferromagnetic core, most of the times we tend to ignore, which is not correct if you want very accurate calculations. So there are two different kinds of approaches we take when we see that the energy stored in the iron portion is also fairly large. Whereas most of the times in many of the calculations, we tend to ignore whatever is the energy stored in the iron portion if it is really negligible. And most of the cases it happens to be negligible. That's the reason we neglect it, right? But we have got basically an expression that is B square by 2 mu naught as the energy associated with the air gap, provided I am already given the flux density, and if I know the volume of the core, I will multiply volume of the air gap, I will multiply this by the volume of the air gap. So this is essentially the field energy associated with the air gap. Right? ID lambda is not really the expression for field energy all the time, unless I am looking at the mechanical moment being 0. If it is 0, yes, ID lambda can be the expression for the field energy, right? So now that we have got the expression for this field energy, I am going to introduce one more term called co-energy, which doesn't have any physical significance, because we are going to use that co-energy also. So let us try to look at what is co-energy. Once we understand field energy, co-energy, and what is the electrical energy input, it will be easy for us to derive the expression for the torque or force. That's the reason why I am first introducing these terms. and I am exactly following the approach of PC Sen. Exactly. So please take a look at that. If you are still having confusion, it will at least clarify matters to some extent. Right? So let us say I am having a magnetization characteristics like this. This clearly indicates that I am drawing the magnetization characteristics for an iron core along with maybe some air gap. If it is only associated with a large amount of air gap, it should have been linear. If I reduce the air gap further and further, it will go further and further towards non-linearity. So this is air gap is large, or primarily we are looking at the air gap. Here air gap is small. And what we are drawing is of course I versus lambda. Now I have completely switched to lambda. I am not writing phi because I am multiplying that by number of turns all the time. Right? So this is what is going to be, the characteristics. Whatever I get as field energy, I am basically talking about this portion. For a given air gap, I call this portion as the field energy. Okay? Whereas, whatever is left over, so if I actually say lambda times I, that is, this is the point where I am going to write this is I comma lambda. That is the point I comma lambda. So if I multiply I and lambda together, I get the complete area of the rectangle. Right? So lambda times I minus whatever is the field energy, I call as the co-energy. What I am trying to do is to actually find out the area of the rectangle, lambda times I, and if I minus whatever is the field energy, which is actually area above that curve along with the lambda axis, that whatever is left over, I call that as the co-energy. So in this particular sense, I am going to have essentially this portion completely as the co-energy. Right? Please note that whenever I am having non-linearity, the co-energy happens to be greater than the field energy. Please note that this is kind of a convex curve. So I am going to have this portion which is actually the co-energy. This is co-energy. So co-energy happens to be greater than whatever is the field energy. Whereas, if I have a linear graph like this, I am going to have basically this as the rectangle, and this line, whatever I have got, is actually the, it is going to be dividing this area exactly into two halves. Right? Because of which I will have, this is my energy, whereas this is co-energy, and this is the plot of lambda versus I. Right? And this is a linear curve. Linear magnetization characteristics. What I have got is linear magnetization characteristic. Because of which I am going to have, if I call this as WF, if I call this as WF dash, so WF will be equal to WF dash if I am talking about a linear magnetization characteristic. Right? So we are deliberately introducing the terminology of co-energy so that we will be able to understand further when a movement takes place. Will we be able to express the force, the torque in terms of co-energy or energy? That's what we want to check. Right? That's the reason why I have introduced this particular terminology of co-energy. Right? There is no physical significance of co-energy, but you may try to write that as lambda di. Just like how you wrote I d lambda in the absence of any movement. We wrote I d lambda integral was actually the field energy. So I would be able to write lambda di integral, that as the co-energy. Right? So I can write in the absence of any movement again, Wf is integral I d lambda, Wf dash will be lambda di integral. Right? But we are not talking about any movement so far. Fine? Now we are going to migrate to a case where there is movement. Okay? So let us say I take the same structure. So this is a C-shaped magnet, and I am going to have one more movable part. This movable part is still stationary because of a spring that is attaching it to a frame. And let's say maybe I have this distance to be x1. Okay? Now I am going to pass a current here. So let us say I am going to pass a current here, some I, because of which some movement is taking place, but still the spring is holding it pretty tightly. So from x1, maybe it is moving to a distance of x2, which is less than the original x1. So it has been attracted, still it has not hit the next one, the actual C-shaped magnet. So it is still in the process of moving. So I probably have this moving up to a distance x2. Originally it was x1, now it is x2. So it has moved slightly towards whatever is actually my C-shaped frame, C-shaped magnet. So if I try to actually draw again the magnetization characteristics for these two distances, this is I, this is lambda. I am going to have actually the first magnetization characteristics probably like this. The second magnetization characteristics will be somewhat like this. So this is corresponding to x1, this is corresponding to x2, because when the distance decreases, I should have definitely more magnetic field or more magnetic flux being there in the magnetic circuit, for sure, because the reluctance has decreased. Right? So this is what is going to be the case. So if I say this is O, let me probably write, maybe at a particular current I am not changing the voltage. So if I actually make the movement pretty slowly, or the movement is happening very slowly, at every point the current would have reached its steady state value, which is V by R, whatever is the resistance of the coil. Please understand, definitely there will be transients in between, because the inductance is changing. As your gap changes, the inductance will change. So at every point, you are going to have a transient response. You guys have studied RL circuit response. If inductance is changing, the current will change, but steady state current will be V by R. Right? Think about it. We'll continue with this in the next class.